Today we are going to cover the last part of the chapter 3, which include conservation of mechanical energy, energy forms, and energy sources. And we already discussed about the different forms of energy, and we say the energy can be transformed from one form to another form, but the energy can be nucleated or destroyed. And this is why the total amount of energy in the universe never changes. Then this is why we can talk about the law of conservation of energy. The law of conservation of energy states that the energy is never created or destroyed. The energy can be converted from one form to another, but the total energy remains the same. Then, for example, the chemical energy we provide to the car, to the engine of the car, this chemical energy is converted into mechanical energy and the heat energy. Then if we add the mechanical energy plus heat energy, this should be the same as the chemical energy we provide to the engine of the car. However, this is the ideal case, yes? Because always there is some loss of energy in the real machines. Then, for example, in this case, we lose energy in form of the sound, and this is then the concept when we analyze systems that are more complicated, then to analyze the conservation of energy is also more complicated because it involves more forms of energy. But here in general, yes, we can say we can cite some of few examples. For example, the three change radiant energy to the chemical energy, or lamp changes electrical energy into the radiant energy and heat energy. Also, the electrical mixer change electrical energy to the mechanical, means motion energy and heat energy. There is here few examples in which we can apply the law of conservation of energy. But again, when we analyze the law of conservation of energy in real systems is more complicated than what we are discussing here, yes, because there are more energies involved in that cases. But in this course, what we are going to analyze is just the conservation of mechanical energy. Now remember, the mechanical energy is the sum of potential energy and kinetic energy. Then the mechanical energy involves just potential energy and kinetic energy. And in this course, we are going to take into account just the gravitational potential energy. Then according to the conservation of law, in case of the mechanical energy, then that states that the total amount of the mechanical energy remains constant in the absence of dissipative forces, means we are neglect the friction, for example, the air resistance, the energy we lose in form of the heat, then we are going to neglect all this loss of energy, which means, yes, the potential energy is converted to the kinetic energy and vice versa. Then in the conservation of mechanical energy, just the kinetic energy is converted into the potential energy, or the potential energy is converted into the kinetic energy. And for example, in this case, yes, in this case, we can, if we think here the car was at rest and in this position, then remember, let me write here the definition just to review. This is how we define the kinetic energy. This is how we define the potential energy. Then what is, if the car is at rest in this position, what is the kinetic energy in this position? Then the kinetic energy in this part is, let's say this is the position 1, yes? Then the kinetic energy in the position 1 equals to 0. Why? Because the velocity equals to 0. But what happened to the potential energy? If we consider this as the reference level, if we consider this as the reference level, then in this case, I will write these equations probably here. Let me write this equation here. And if we consider this as the reference level, then this will be 0. And this will be the height we are considering. Yes. Then in this position, the potential energy will be, and the kinetic energy will be 0. But what happened with the car is moving down, the car lose potential energy but gain kinetic energy. But in this point, what happened with the potential energy? The potential energy equals 0. And why? Because H equals 0 in this point. Let's call this the point 2. And in point 2, because we choose this as the reference level, in this point the potential, then all the potential energy was converted into the kinetic energy. And then we can calculate. Here, this car has some velocity. And the same happened when, in the case of the ball. Yes, in this case, if the ball in this point has some potential energy, when the ball is moving down, the potential energy is decreased and gain kinetic energy. And if the ball is moving up, then the kinetic energy is decreasing, but the ball is gaining potential energy. Then let's analyze this situation. Remember, according to the conservation of mechanical energy, always the mechanical energy must be constant. Means if we add the potential energy plus the kinetic energy in any point, if we analyze in any point, then that should be equals to a constant value. Then here, probably we should write here, this one is constant value. Why? Because the potential energy is converted into the kinetic energy, or the kinetic energy is converted into the potential energy. And if we add these two energies at any point, we should get a constant value, always the same value, because we don't lose or we cannot create or destroy energy. Just one energy is transformed into the other energy. And let's see what happened in this case. We had this ball. Yes, we had this ball. This is the ground. This is why we select this one as the reference. This is the. Then what happened in this point? We call this one, this is the point 1. This is point 2. This is point 3. Then what happened in this point? If this is the reference level. In this case, we are holding the ball. Yes, the ball is not moving. Then in this point, in point 1, let's say this is the point 1. In this point, what happened? The potential energy is maximum in this point. But because the velocity is 0, there is no kinetic energy. This is why here we had the potential energy is the red bar. And this is why the potential energy is maximum, but there is no kinetic energy. This is why here the kinetic energy is 0. And the reason in this point, the velocity equals to 0. What happened exactly in the middle of the trajectory when the ball is coming down? And in this point, the ball loses some potential energy because the height is decreasing. Yes, here is just half. But that potential energy that was lost by the ball was gaining as kinetic energy. And this is why here the potential energy and the kinetic energy is half and half. Yes, we had 50-50%. Now, what happened in this point? In this point, we know the potential energy equals to 0. And we know that because the potential and the height equals to 0. And in this case, the potential energy equals 0. And probably I will write here the velocity is 0 and here h is 0. But because of the potential energy was converted into kinetic energy, then we can say in this point the kinetic energy is max. Yes, it's the maximum kinetic energy. And let's see here if we just write some number. If just say the energy in this point is 5 joules, then all the potential energy, all the mechanical energy is potential energy. Means in this point we know the potential energy is 5 joules. Then what will be the mechanical energy in this point? Should be 5 joules because it's constant value. Means this should be 2.5 joules. If it's 50 and 50%, then this is 2.5 joules. And if we add this together, equals to 5 joules. Why? Because of the conservation of mechanical energy. The potential energy was the potential energy was converted into the kinetic energy in this case. And what will be the mechanical energy in this case? 5 joules. But in this case, all the 5 joules that was potential energy was converted into the kinetic energy. Then in this point, the potential energy is 0 and the kinetic energy is 5 joules. And if we add this together, we will get 5 joules. Then this is why the mechanical energy should be equals to constant value. And in this example, equals to 5 joules. We had one more example. Here we had the simple pendulum. In this case, we are analyzing what happened with the energy of the pendulum when the ball falls through this distant edge. Yes, when it's moving from here to this point. Then what happened in this point? In this point is like we are holding the bob. Yes, we are holding the pendulum. And what happened is in this point, the kinetic energy equals 0. Why? Because the velocity equals 0. Yes, this is why the kinetic energy is 0. Remember, kinetic energy, maybe I will write here, kinetic energy and potential energy. Means in this case, all the energy is potential energy, as in this point. Let me write here. But now, what happens if the ball is moving down? If the pendulum is moving down, then in this point we will have 50 and 50%. Yes, we will have 50% potential energy, 50% kinetic energy. And part of the potential energy was converted into the kinetic energy. But what happened exactly in this point? Yes, what happened exactly in the middle of the trajectory of the pendulum? And what happened is the potential energy equals to 0. And why we can say that? Because we can remember, we can select the reference level we want. And in this point, we select this one called 0. And in this point, the potential energy is 0 because the high equals to 0, but the kinetic energy is maximum. This is why, because if the kinetic energy is maximum in this point, then this is why in this point the velocity of the pendulum is maximum. Yes. Because this is the maximum kinetic energy. And if we had the maximum kinetic energy, we will have the highest value of the velocity. And we can see what happened during fall is the potential energy lost is gained up kinetic energy. Yes. Then the potential energy lost is gained as kinetic energy. Then here I want to do a little more math in which we can apply the conservation of mechanical energy. Then let's think again in the pendulum problem. Then here we had here, and this is moving to this point. And this is the h distance, and we will select this one as the reference level. Means this is the h equal 0. Then we will analyze 2 points of the trajectory of the pendulum. We will analyze this is the point 1, and this we will say this is the point 2. And we know if we, according to the conservation of mechanical energy, if we add the mechanical energy in any point, we add the potential energy and the kinetic energy, this value should be equals to constant and should be the same in any point. Then, according to that, the mechanical energy in the point 1 should be equal to the mechanical energy in the point 2. And remember, the mechanical energy is the potential energy plus kinetic energy. And just we are saying 1 and 1 because it's the point 1 is here, and then it should be equal to the potential energy plus kinetic energy in the second point, where here. And just we wrote here the definition of the mechanical energy. Then what happened in this point? And we assume in this point the velocity equals 0. Yes, it's like we are holding, so we can imagine we are holding the pendulum. Yes, and in this point the velocity is 0, and this is why the kinetic energy equals to 0. But what happened in this point, because there is some height, then we had some potential energy. What potential energy? But in this point, what happened? Height equals 0, and this is why the potential energy equals 0. However, the kinetic energy is not 0. That's because all the potential energy was converted, was transformed into the kinetic energy. And in this point, the kinetic energy depends on the mass of the boat and the velocity of this pendulum in this point. And usually we can refer to this one as the maximum potential energy in this point. You can say this one, this is the maximum potential energy. In this point, this is the maximum kinetic energy. This happened in point 1, and this is what we had in point 1. Then let's try to bring this to the equation. Then in point 1, the kinetic energy equals to 0. Then this equals 0. Yes? Because in this point, the kinetic energy equals 0. Then let's see what happened, and the potential energy is just mass times g times the height. What happened in the second point? What happened in this point? The potential energy equals 0. Then this value is 0. Then we had the kinetic energy, and the kinetic energy is 2. Now, let's see what happened in this case. If we want to solve for the velocity, if we want to know what is the velocity of the pendulum in this point, then we can solve for the velocity. And what we can do is we can divide by the mass. I will do it on this side, this part. Let me write again this equation. And we can divide by the mass on both sides. This cancel out, and we will have here if we want to solve for the velocity, we can multiply by 2 on both sides. Yes, we can multiply by 2 here, multiply by 2. This cancel out, and then, sorry, here is g. It should be g, no. Yes, mass cancel out. Here is g. Then now we had 2. And now we can take the square root on both sides to solve for the velocity. Then now finally we had 2 multiplied by the acceleration of gravity times I square root equals to the velocity. And the velocity of the pendulum in this point, we can see depend just on the height of the pendulum. Doesn't depend on the mass of the boat. It depends just on the height of the pendulum. And the reason is the reason the velocity is independent of the mass is because the main force acting on the pendulum is the gravity force. Just remember if you release if you release two objects with different mass at the same time, they will hit the ground at the same time. Yes, doesn't matter what is the mass. And this is similar effect happen here. If the force acting on the object is just gravity, then the results are independent of the mass of the object. And this is happening in this case. Yes, the velocity is independent of the mass of the pendulum. And this is what we had here is the potential energy lost in this point equals to the kinetic energy gain in the other point. And this is what we had here in this point. Yes, this is what we got here. And this is why we got the velocity equals to the velocity on this point depends just on the height of the pendulum. And let's try now to solve some problems in which we can apply all we discussed before. And here we had two problems, but they are related. Then let's solve the first problem. We had a 1 kilograms book falls from the height of 1 meter. Then what is the velocity just as it hits the floor? And we had a book here. Yes, we had some book here. And this book is 1 meter. It's 1 meter. And this book falls. And we know the mass of this book is 1.00 kilograms. And we want to know what is the velocity of the book just in this point. Yes, just when the book hit the ground. We want to know what is the velocity in this point. Then we can use the conservation of mechanical energy to solve the problem. And just to review, I will repeat again how we can get using the conservation of mechanical energy. And in this point, we assume in the point 1, let's say this is the point 1, and this is the point 2. Someone was holding the book, yes, and this is before the book falls, or just the book was at rest, this was not moving, then we can assume here the velocity equals 0. But when the book falls, then the velocity was increasing, and here was reached to the ground at with some velocity. And we don't know this is the velocity we want to calculate. And in the point, if the velocity is 0 in the point 1, we know the kinetic energy in this point must be 0. But the potential energy in this point should be mass times g. What happened in the second point? If we choose this as the reference level, then in this point h, the height equals 0. And what happened in the second? The kinetic energy equals to this velocity, but this is point 2. The potential energy in this point should be equal 0. Why? Because the height equals 0. And what happened is the potential energy was converted into the kinetic energy. And this is why we can say also the loss in potential energy is the gain in kinetic energy. And if we apply the conservation of mechanical energy, then we should start with we say the mechanical energy should be the same in any point. But the definition of mechanical energy is the potential energy in this point plus the kinetic energy in this point should be equals to the potential energy plus kinetic energy in any other point. But we know this kinetic energy, this is 0, yes, this is 0. And we know the potential energy in the second point also is 0, is this one, yes, is this one. Let me remove this line. And finally, we have and also in some books you can say this is loss and gain. This is the same idea. Yes, the potential energy loss is the same as kinetic energy gain. And if we just replace by the equations we had here, then we had potential energy in the point 1 equals to this one, to mass times g times the height. And the kinetic energy in the second point is half multiplied by the mass multiplied by the velocity just in this point. We divide by the mass, this cancel out, and we will have. Now if we want to solve for the velocity, we multiply by 2 on both sides, then we multiply by 2, multiply by 2, this cancel out. And to solve for b, we take the square root on both sides. And here we have 2. And let's write here. Then now, yes, we can solve. Yes, we can calculate the velocity with the information we know. Then it's square root 2 is a constant value. G, we know this one is 9.8 meters per second squared times I is 1.00 meters. Then if we calculate, we multiply this together, let's see, we will get is 19.6, we'll get the square root, 19.6 meters times meter will be meter squared over second squared. And this is the units we expected with. Once we take this one out from the square root with the meters per second, which are the units we expected for the velocity. And in this case, this will be 4.43 meters per second. And this is the velocity of the book in this point, yes, in the point 2. Now let's try to solve the second problem, which is related to the first one. And in this case, we want to calculate what is the kinetic energy of this book, yes, of the 1 kilogram book, just before it hits the floor at 1 meter fall. And we want to calculate what is the kinetic energy in this point. And in this case, because we already know the velocity, then we can use this value to calculate the kinetic energy. And let's do it in the next page. And in this case, we say this is the point 1, this is the point 2, and we know the velocity in this point is 4.43 meters per second. And now if we want to calculate the kinetic energy, because we know the mass is 1 kilogram, and we know the height is 1.00 meters. And we can calculate the kinetic energy just in this point, in the second point, yes. This is where we want the kinetic energy. Then its mass will be 1.00 kilograms. Then now we want, and here is a square. We need to square the velocity. Then if we calculate the square of this one, then we will have the kinetic energy. And I will just write step by step just to analyze also the units, and will be 19.6. And we need to square the number and also the units. And if we calculate the kinetic energy, we will have, we need to divide by 2, will be 9.81 kilograms. And we know these units correspond to joule, and we can write the kinetic energy in the second point equals to 9.81 joules. Then this is one way we can solve the problem. Way 1. But also we can solve the problem without calculating the kinetic energy. And if we don't know the velocity, then we don't need to calculate the velocity. If you know the velocity, just use that value. But if you don't know the velocity and you had similar information, then you can calculate the same value, but just applying the conservation of kinetic energy. And let's try to solve in the other way. And this is the situation we had. Here we had and what happened is we know now the potential energy in this point is maximum. There is no kinetic energy. In this point, the kinetic energy is maximum. The potential energy equals to 0. And that happens in the point 1 of the potential energy is converted into the kinetic energy in the point 2. And this is why we can say in different ways this. And the potential energy maximum equals to the kinetic energy maximum. Or you can say also the potential energy lost equal to the kinetic energy gain. Or you can say the potential energy in point 1 is the kinetic energy in the point 2. These are different ways you can find the same expression and all are the same thing. The meaning is the same thing. Then it's just I want to show the different ways. This is when you read in your book, you will understand what is the meaning. And if we know the kinetic energy in this point equals to the potential energy in the point 1, what we can do is we can calculate the potential energy and we will know the kinetic energy. And let's do this one first. We can calculate this potential energy and then we will know the kinetic energy. And the potential energy in the point 1 is 1 kilogram, 9.8 meters per second squared times 1 meter. And we see the potential energy. We multiply these numbers together is 9.8 kilograms second squared. Yes. And we know this value 9.8 joules. But we know this value equals to the kinetic energy. So the kinetic energy 9.8 joules. Finally, there is this is the two different ways we can calculate, and there is the two different ways we can calculate the kinetic energy. If you know the velocity, just use that value to calculate the kinetic energy. But if you don't know the velocity, then I think it will be easier just if you calculate the potential energy and then the potential energy equals to the kinetic energy. Yes, it's easier. And now you know you have these two different ways how to solve the problem. Now we had one more example. Then we want to know how much work is done in moving a 2 kilograms book to shelf 2 kilograms meter high. And we want to calculate the work to move a book as we want to move this book 2 meters. We want to move the book from this point to this point. And we know the mass of the book equals to 2.00 kilograms, and this is the height equals to 2.00 meters. Then we want to calculate the work, but work equal to force multiplied by the distance. Then we don't know the force, but we know to move the book, we need to work against the gravity. Means in this case the force equals to the weight, and in this case the force equals to mass times g. Then we can write the work force is mass times g value. Also, because d in this case is high, then you can write also this equation like that. They are the same thing, yes? It's the same information you have. Then now we can calculate the work. Mass will be 2.00 kilograms. G value will be 9.8 meters per second squared. And then the height will be 2.00 meters. And if we multiply these numbers together, then we will get 39.2 kilograms meter squared, meters times millimeter squared. And we know this corresponds to joules. Then the work will be 39.2 joules. And this is the first part of the problem. In the second part, we want to know what is the potential energy of the book. And remember when we say when we if we lift something, then we are doing some work on this object. But in the same way, when we lift the object is gained potential energy because of the work we are done on the book. Yes, this is why in this case, when we are doing some work, that work is giving potential energy to that object. Yes, and this is why in this case you can solve this saying like that. Yes, because the work you done on the book, yes, the work you done on the book to move here, it gives potential energy. Yes, it gives potential energy, and you can say the potential energy should be equal to the work. I want to look. Then the potential energy equals to 39.2 joules. Also, you can use the equation of the potential energy to calculate. Then the potential energy mass times g, and you can see the equation of the work and the potential energy are the same equation. Yes, it's the same equation. This is why you will get the same thing. Yes, you will get here will be 2 kilograms, 9.8, and this is why the potential energy in this case will be equals to the work. And if you know the work, and you don't need to calculate again, you know the potential energy. And in this case, the potential energy equals to the work because they had the same equation. Yes, work also is. Then let me write like that. Then this is why I don't going to do again the calculation because it's the same. Then the potential energy in this case will be 39.2 joules. Now, how much kinetic energy will the book have as it hits the ground when it falls? Then what happened in this case, we say, probably we will use the same. Then the potential energy in this point we know is 39.2 joules. Let me write again these numbers. The potential energy is 39.2 joules. Oh, it's not good. Then what happened? What will be the kinetic energy in this point? Do we need to do any calculation to know what is the kinetic energy, or we already know what is the value of the kinetic energy. Remember, by the conservation of mechanical energy, all the potential energy lost is gain of kinetic energy. Then by the conservation of energy, we know the kinetic energy should be 39.2 joules. Let me write this number. 39.2 joules. And we know the kinetic energy must be also 39.2 joules. And let's write here, by the conservation of the mechanical energy, we know the potential energy in the point 2 equals to the kinetic energy in the point 1. Yes. Doesn't matter what you choose, what is point 1 or point 2. Now this is just to level, yes, to have some order, but doesn't matter what is point 1, point 2. Then, or you can say also the potential energy loss equals to the kinetic energy. Okay. And we know the potential energy is 39.2 joules. Then the kinetic energy must be 39.2 joules. Then we can see in this situation work the kinetic, let's see, the potential energy, we say loss, or remember you can say maximum, any of this equals to the kinetic energy. Okay, or you can say also maximum. Let me write this one smaller. I want to write here the value. Equals to the kinetic energy. Okay. Or we can say also maximum, and this equals to 39.2 joules. And you need to analyze each problem, but you can see if you use the conservation of mechanical energy, you can save time, and you can avoid calculations. Yes, because in this case, if we calculate the work, we know the work equals to the potential energy, and the potential energy equals to the kinetic energy. Then we don't need to just do one calculation to solve the problem. Now let's review some energy forms. Yes, we are going to talk a little about the different energies, different types of energy. Then we already discussed the mechanical energy, which is the sum of the potential and the kinetic energy. Yes, and we discussed also using the conservation of mechanical energy. We know the addition, the sum of the potential and kinetic energy should be the same in any point. It should be the same in any point when we are analyzing any system. The other form of energy is the chemical energy, and this energy is the energy associated with chemical reactions. Then in this case, we had some examples here. We had the battery, and we know that in this case, the chemical energy inside of the battery occur chemical reactions that we can use the energy released due to these chemical reactions, we can use as electrical energy. Also, in this case, we had wood and coal, and this coal and wood they store chemical energy through the photosynthesis process. In this case, we had chemical energy in the wood that we can use as heat energy. For example, we can transfer chemical energy into the heat energy. And here, this is in case of the coal, we had that photosynthesis process happened millions years ago. Yes, then that energy is stored in this kind of material in coal, and this we can use, for example, to convert this chemical energy into the electrical energy. And now we have the radiant technology. This is a form of energy that can travel through the empty space. It's called also electromagnetic radiation, and the visible light is just a small part of the electromagnetic radiation. Right now, the scientific community, they are trying to develop some technology that they can get the maximum percentage of solar energy that can be used as, for example, electrical energy. Means they want to improve the efficiency of the solar panels. They can get more energy that can be converted into another kind of energy, like, for example, electrical energy. And here is a little more about the electromagnetic spectrum, and we can see the radiant energy include not only visible radiation, include another kind of radiation. We will talk a little more about this one in the next chapters. And we can see also the visible light is just a small part, it's a tiny part of the electromagnetic spectrum. Another kind of energy is the electrical energy, is the energy that comes from electromagnetic interaction. The fossil fuel are the primary fuel for electrical generation in USA. This how we convert the fossil fuel into the electrical energy. Then this is that happen in the fossil fuel nuclear power plants. In this case, the coal and natural gas is converted or is produced steam. We burn that material and then produce steam. And this is how chemical energy is converted into heat. Then this heat passes through the turbine, and the heat is converted into mechanical energy, motion energy. Then in the turbine, this mechanical energy is converted into the electrical energy through the generator. And after that, this electricity goes to our homes. Yes, this is how we can get electricity in our homes. The only problem with this is the fossil fuel power plants are not clean energy. They generate a lot of carbon dioxide. Another kind of energy is the nuclear energy. Is the energy that comes from the nuclear reactions in an atom. Then this energy is generated in nuclear power plants, and the way the nuclear energy is converted into electrical energy is the similar way is a similar process occur in the fossil fuel power plants. But in this case, the energy, the primary source of energy is the nuclear reactions. Yes, is the nuclear energy instead of coal or nuclear or natural gas. In this slide, we had the energy consumption in USA from 2015 to 2018. And there are maybe 3 things I would like to analyze from this different data we had here. First is the total energy consumption, and we can see good thing was almost the same except for the last year, for the data we had for the last year is around 100 British thermal units. These are units for the energy in the English system. Then this is one thing I would like to check as that value. The other thing we can analyze is most of the energy is obtained from fossil fuel. Yes, we had see here is we had petroleum, we had natural gas, we had coal, and just 9% correspond to the nuclear power plants, and 10% correspond to the renewable energy. And this was in the last, from 2015 to 2018, we had similar values. There's now too much changes. Case for renewable energy, just 1% in the last 2 years we had here. And another thing I would like to just pay attention is the renewable energy. The percentage of the energy obtained for renewable energy is just 10%. Yes, it's just 10%. And let's now think how large is a quadrillion British thermal unit? How much is 1 quadrillion of British thermal unit? Then the consumption is USA is 100 quadrillion British thermal units. And 1 correspond to can be 45 million tons of coal, 1 trillion cubic feet of natural gas, or can be 170 million barrels of crude oil. Then this is huge, as that numbers, even is difficult to imagine that number. But is huge amount of energy. And if we analyze this data we had here for energy use per capita in different countries, we can see US is one of the countries where the energy consumption is high. Yes, it's just first is Canada, then is US. Then it's something that it's good to think about that. It's good to think how we can help to change that. And probably we can say we cannot do anything, but I think even if we can do small things, we can contribute to that number change. And why we want this number change? First, because the energy source are limited. The fossil fuel are limited. There is one moment this is going to it's not going to happen maybe in the next 10 years, but we need to think in the future generations. And then this is something we need to consider. Then the other thing is we are not doing much to get different source of energy right now. Yes, it's just 10%. Or maybe it's not easy, yes, to get that amount of energy right now with the technology is available to get more energy from renewable source. Then what I can say now is, even if we can do small things, and one small thing we can do is recycling. Because to produce plastic bottles, to produce cans, everything requires energy. And if we can save that energy, then it's something small things we can do, but we can do something. Then what I suggest you is, you are not recycling in your home, just start recycling probably just plastic for 1 week, and you will see how much plastic we produce in 1 week. Then I suggest you try to start recycling just one thing, and then for 1 week, and then you can see you can do something. It's a small thing, but you can do something. And the last thing I want to emphasize is to say this is the energy source we are from where we are obtaining energy right now is for fossil fuels. This is the main source of energy right now, and hopefully this will be the energy source for tomorrow. Then we expected that with the technology that is emerging, this can increase the amount of energy that is obtained from the renewable source of energy. And the main thing is because, again, this source of energy are limited, but also because the renewable source of energy, they are cleaner compared with the fossil fuels, because they emit less carbon dioxide. This is all I had to discuss today.